All right. You guys hear me? Yeah, maybe. Hear me? Yes or no? All right. Thank you. I know you guys can probably hear me. All right, so let's get started. Sorry, but if I don't eat between classes, I lose the opportunity to eat until 5 p.m. and I'm not willing to do that. So good stuff. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. Pray that you would give us clarity of mind, give us the things that we need to be successful. In your name we pray. Amen. All right, so what are we doing today? Stuff and things, right? Let's recap, then we're going to jump into topic 5, which is the Laplace transform. All right? The Laplace transform. So by way of recap, the whole Simulink, sure. Second order matrices, okay. Simulink. It's mostly Simulink. People are not getting Simulink. It's not surprising. We've spent like a week on Simulink, and Simulink is one of those things that you just need to do to learn how to use it. Frankly, it's like SolidWorks in that regard, right? You can listen to me talk to you all day about how to do Simulink, but until you actually try it, it's not going to necessarily click. If you are trying the problems for homework, and you're coming up, you're taking big swings and missing, right? That's okay. But, ask me, ask questions, come to office hours. We don't have office hours over the weekend, Dr. D. That's true, I don't, because that would be ridiculous. But I do have an email address that you guys can all use and you'll have access to. And if you send me a question on the weekend via email with like a picture of your work, I can try to help you, right? It's not going to be as instantaneous, right? But my kids do still nap for a couple hours in the afternoon, so I can probably squeeze out a couple responses during that. Or at night, right? So it's worth a shot. Worth a shot. As Dr. Staggs would say, it's worth the price of the question. Worth the price of the question. Second order matrices. And that's not really. I'm confused by the confusion. When we have a second order system, our A matrix is going to be a 2 by 2, right? Our B matrix will be a 2 by 1. Second order doesn't really. Second order matrix will be 2 rows by however many columns it needs to be, right? The reason that A is a square matrix always and forever is because we have as many rows as we'll have columns, right? Why? Because our state variables, because x and x dot are the same, just one is the derivative of the other, right? So when we make our x dot is equal to ax plus bu equations, x dot has the same number of variables in it that x has in it because you derive one from the other, right? And so that's why when you have a second order system, right, you have x dot 1 and x dot 2 as your x dot vector, x1 and x2 as your x vector. So you have 2 by 2a, a 2 by however many inputs you have, b, and then c and d are determined by the number of outputs that we're trying to define. Okay. Again, matrices aren't really the point of this class, right? The point of this class is the building of the models and the testing of the models, right? If you have more questions about like the linear algebra stuff that we're doing, please feel free to stop me at any point and ask if it's relevant to what we're doing, right? Because I am, to be quite honest, a little bit confused about that on there. Okay. We are going to do more Simulink today. Right? It's not just Laplace transforms. The whole first part of class is us talking about integrated systems, and you guys are going to do a problem, right? You guys are going to try some stuff, and it's not. Right, so let's just get into it. You guys have any other questions or anything that you want me to go over before we start? Yeah, Foster. So say that one more time, sorry. That's a good question. So why are there different amperages in the lab? Essentially, the power supply limitations. We went up to 7 on the first trial and then backed it off on the second. It's just how the power supply responded when we were doing it. We tried to get it as high as we could. It's not a super great power supply. We'll talk more about the lab on Tuesday. We'll do a demo like in class. I know that doesn't really help you guys, but if you want, before you leave, it's right there on the back wall. You can see the actual setup and everything that we do. The point of the lab, right, is to come up with a model and then test it versus what actually happened, right? So you need to know those parameters. So I owe you guys still, right? I owe you guys B and K for the dampers and the springs that are on there for the shocks, and I owe you motor curve, which I have. I just haven't posted the loud file yet. And I'll get to that this weekend, or probably today. Okay. Any other questions? Now remember, lab in groups of 2 to 3. Integrated systems, right? We talked a little bit about integrated systems on Tuesday. Why do we want to use integrated systems? Well, we don't necessarily always need to use integrated systems, right? Integrated systems are a nice way for us to clean up our models if they're really complex and it's hard for us to tell what's going on. But they're not a necessary thing, right? They're not necessary. But if you have something that's super congested and you really just can't tell by looking at it what's happening, maybe grouping it as subsystems would help. And how do we do that? There's 2 ways. First, we can create each subsystem separately, and then we can use the bounding box, which is not the way that I'm going to show you because it's convoluted, in my opinion. But if you want to learn about bounding boxes, Appendix C of the text is a great place to check out. So what we're going to do is we're going to use the subsystem block from the ports and subsystems library. So pretty sure I flashed this example before we left for okay, right? So we're going to be doing everything in the context of this solenoid again, right? And if we were following along on Tuesday, basically everything we did on Tuesday was in the context of the mechanical portion of this solenoid model, right? We talked about doing it as a transfer function. We talked about doing it in state space. We did it as an integrator block. We included nonlinear components in an integrator block, right? And now, look, there's our model, right? mx double dot plus bx dot plus f dry signum of x dot plus kx is equal to some force electromagnetic. Right, FBM is equal to 0.5 Ki squared. And we can come up with the solenoid coil model, right, the electrical portion. And we've done this before. Turns out that it's Li dot plus Ri is equal to En of T Ki x dot. Okay, and that's what we get. Okay. We also have some parameters associated with this. Now we're going to. So probably take note of that. Take note of these parameters. We've got the resistance, the inductance, the back EMF constant, the armature valve, the viscous friction, the spring constant, and the drive. So we want to model this in Simulink, right? And we already have half of it. We have the mechanical half, right? From class on Tuesday. We know what that's supposed to look like. We've got some very varying parameters from what we had on Tuesday. But overall, right, we have the model itself, so changing the parameters isn't such a big deal. But how do we get the block diagram for this, right? For Li dot plus Ri is equal to En of T Ki x dot, right? Well, how do we get this? Well, we can do it a couple ways. Right? We could do the transfer function method, and that would work, kind of. Except that, what do we need? Well, we need x dot to feed in from our mechanical model, and we need to create some electromagnetic force based off of the current output, right? Because the electromagnetic force is 1/2 times K times I squared. All right, so how do we do this? Well, I'm going to propose that we use an integrator block method, right? And I can solve this. Well, let's just solve it for I dot. I solve this one for I dot, right? And I'll get 1 over L times En minus Ki x dot minus R times I. Remember, when we're doing the integrator block method, what we want to do is start by almost creating the state variable equation, but we're going to stop short and we're not going to create state variables, right? We're just going to solve this for the highest order derivative. We did the same thing for this model, right, when we made it, right? We came up with x double dot was equal to 1 over m times FEM minus b over m x dot minus f. So that doesn't need the over m, right, because it's all on the outside. Let's try that again. Minus bx dot minus f dry signum x dot minus kx, right? I realize that is sloppy. I just do not have enough room to write that. I apologize. All I've done is I've taken the equation on the right and solved it for x dot, x double dot, right? That's all I did. Solved it for the highest order. Okay. So far, so good, right? Everybody's kind of tracking. Any questions so far? Why we want to do this way? SGN, that's the signum function, right? That's going to return, so SGN is the signum function. It's going to return -1 when we have a negative number there and +1 when we have a positive and 0 when we have 0. Okay. Let's look here. I've got my integrator block for my mechanical system, right? This is the same model that we came up with towards the end of class on Tuesday, right? Symbolically, then that's just plugging in a number once we get it. So we've got this, right? This is inside of my subsystem block. Now, zoom, super rude zoom. Let's try that again. right? So I've got this little bubble that says FEM. That's obviously my electromagnetic force, right? And what am I feeding out of here? Well, I've got the X position, right, in that top little bubble there, and X dot in the bottom one. What are those? Those are my input and my output ports. So let's talk about subsystem. Right. So you can type subsystem, right? You pick the top block here. And look, it gives me this, right? Notice it looks exactly like the other ones that I have there saying mechanical and electrical, right? And inside, it looks like they're kind of transparent a little bit, right? They're opaque. You can kind of see in there, and then you can see it comes with one input and one output. Notice that the block itself also has one input and one output, right? So what if you wanted more? Well, there's a couple ways you can do it. Or you can go to signals and ports, add output signals, right? Or if you double click inside, right, to open it up, you've got one and one, right? So you can disconnect this, right? And you can move them around. But if I wanted an extra one, I could copy it, click Control C, Control V. And I can have as many as I like, right? But when I come back out, which you can either use this toolbar and click, right? Notice now I've got 4 inputs, right? It automatically tracks them. And if you label your signals, if you label these things, it will automatically pull in a label for what the signal is. So let's go back in here, right? We'll get rid of everything that's in there. And if I do that, look, the block is blank, right? And if you were to take all of your stuff from the initial diagram here, right? Oop. Double click to get inside, then notice, right? This is the block. This is the block diagram that we had from class on Tuesday, and I just copied it, pasted it, put it into the subsystem block. Now it's a subsystem, right? But now I don't have inputs and outputs, right? Oh man. So let's go up here. We'll go to our library. You can't see the library. I click the library button. You go to ports and subsystems. And then you can have an in or an out, right? So if I drag my in over here, I can drop it right there. Look, there's an in. Number of ports, port number, right? You can assign that. We're just gonna leave it as 1. What if I typed out? So instead of going back in the library, I'll just type out. Yep, we'll take out 1, right? Put it there. I don't feel like typing it again. Copy, paste it, put it here. Come back out, I've got this stuff. How do I know that I want that to output position and velocity? Right, how do I know that? Here's how I know this. We look at the equations, right? We look at the equations. X dot needs to come back and feed into the back EMF, right? X dot is creating the back EMF. Our equations are coupled, so our subsystems are coupled in some way, right? The electrical system produces FEM, the mechanical system produces the back EMF, or what is used to produce the back EMF, right? Produces that X dot, and we go round and round in a loop. And you can see it here, right? X dot is coming up, and back around is an input to my electrical system. Okay. All right. What about this electrical system? All right. So let's talk about the ground effects that I'm getting here, right? Why am I getting red fluorescence around these blocks? Well, I haven't defined any parameters yet. Notice, I've left it as a variable, right? It says 1/L on here. I haven't defined what L is, and I think I went over this a little bit right? But you can use MATLAB to define your workspace variables, and then those variables will get transferred, or will get pulled by Simulink, right? Because Simulink runs MATLAB in the backend, and they share the same workspace. So I'm going to define all of these in MATLAB in a second before we run this. All right, so we have our equation, right? Our equation was I dot is equal to E in of T minus Ki x dot minus Ri all times 1 over L, right? So what do I have here? Well, here's I dot, right? I dot, well, that's equal to E in minus I times Kx dot. This is a new block that we haven't talked about though, right? This guy. This is the product block. Why can't we just use a gain block, right? We're multiplying these two things together. Well, we're not multiplying it by a constant, right? You're multiplying two different signals together. And what the product block does is it takes two different vectors and it multiplies them element-wise. And what that means is that it'll take the first entry of each one and multiply them together, the second and multiply them, and so on all the way down the line, right? Until we stop running our simulation. So it's going to essentially run this multiplication at every time step, right? For these two signals. This creates my back EMF, and then this signal is just R times I, and those all get subtracted. The whole thing gets multiplied by 1 over L. That gives us I dot, right? I take the integral, this becomes I, right? But that doesn't give me FEM, right? Because FEM is K times 0.5 times I squared. Well, here's another new block. Here's the square block. What does it do? It squares my signal. So that's I squared, right? Here's I squared, and look, you can do, oh, the square block does more than square, right? It does a lot of different things. You do log, exponential. This gets multiplied by my gain of 1/2 times K. And then that gets exported as FEM, right? Remember, that's my output node, right? So that's the signal that's coming out of this block. That gets pushed into my mechanical system, and so on and so forth, round and round and round, right? This is just feeding back. Okay. Do you absolutely need subsystems? No, right? You don't. But like I said before, this looks a lot cleaner than if you did this without subsystems. Okay. All right. Do you guys have any questions on the makeup of this? So the question is, how did I get my variables inside of, like, how did I get this to say, I got to use the right mouse, hold on. Oh, also should use the correct screen. That's also super helpful. Let's see. All right, here. How did I get this to have FEM in there, right? So, first of all, right, this is port number 1. If you double click it, you can tell it to display the signal name or the port number. So I just clicked signal name. How does it know what the signal name is? Because I named it right here. So whenever you name a wire, right, you're naming the signal in that wire, right? So I know FEM is coming out right here, and because I put it into this block, right, instead of having it as, I think it defaults to port number, and you could also do port number and name, right? That's a little congested though, right? It defaults, I'm pretty sure, to port number, so it just tells you this is 1. Yeah, so if you need this block, right, if you don't have one in here and you need an out, you just type out. right? And then out 1 comes up. Same deal, you can come up with in, right? The command is in and out. All right, we get those labels by actually labeling our signal. Otherwise, it'll remain as it defaults to the port number. Right? Port numbers are also nice sometimes because if you're actually using this to connect to a real world device where that connects to a DAC port, right? You can keep track of what connection is supposed to be where, right? This is supposed to exit to port, analog out 1 or whatever, right? So keep that in mind as well. Any other questions? Okay. Well, if we don't have any other questions, I'm going to go ahead and I'm going to pop these values directly in the map. Right? So I've done it before. These are the values that I gave you on those slides, right? If I hit enter, hey, this time it actually worked. Last class, it didn't even show my workspace right here. You can see my workspace is populated now, right? Great success. My workspace has populated. I can go back to my Simulink model. And when I do that, everything should turn not red. So what was in here? Right, this is a step of 0.05 that goes up to EN. Right? We can run this. I'll hit run. And there's a couple of cool things that we can do here. He says, well, first of all, let's look at this scope. This is the position of the solenoid. We gave it a step of 10 volts. And interesting. Why is this interesting? Well, you can't really tell from this far out, but this kind of looks like a first order response, right? Kind of looks overdamped. But there's this part right here, where it kind of looks like it goes up. Now, is that a trick? Is that a trick by optical illusion? It's not. It is not an optical illusion. It's actually increases at that point. There's like a second sinusoidal response happening at that point in time. What the heck is that? Yeah. That, ladies and gentlemen, is the nonlinearities in the system doing weird things. Okay? But it can also be attributed to what? Right? This is a third order system. So we've got a first order and a second order system. Right? The second order system is where these oscillatory dynamics are going to come into play. So potentially the time constant of the second order system was long enough that it didn't take over until, a quarter of a second, 0.22 seconds, whatever this happens to be. Potentially, could be. Right? But it's more than likely due to the nonlinearity in the system, right? Because what happens? We overcome some friction, and then you would expect that the position would increase, right? You're going to have a little bit of a spike after we get out of static friction to kinetic friction. Right? Okay. So that's neat, right? That's neat that we had some weird things going on. There's also another thing we can look at. Nope. Or maybe we won't. Who knows? We can also look right here. This one is particularly strange. This is my electromagnetic force. The output from my electrical block. This is weird looking, right? What was that, Charlie? So again, remember, this is nonlinear, right? This is a nonlinear model. So we get this weird, it turns on and then it spikes down, and then it comes back up, right? And then it oscillates, right, at steady state. All right, we start to see some weird oscillatory mechanics start to take over around here. Right? But this, let's talk about this, right? So the force comes up, then it drops a little bit. Right? Why? Well, that's probably where we broke friction. Right? That's probably where, because remember what the friction curve looks like, right? You increase till you hit the max, and then you're going to drop, and your friction's going to plateau, right? So we hit some maximum frictional force, it instantaneously flips to kinetic friction, which is a lower amount of friction. So we have that traction there, and then we come up. All right, and then we have some, because it's third order, remember third order systems are just a combination of first and second order systems, typically. And so the oscillation comes from our second order dynamics, which take over at a much higher or at a much later time. The other thing that we can do is we can look at that x dot graph, right? And here's my x dot graph. That's the graph of my velocity. And so we get a large input, and then it dies off until we have steady state, right? So we have a large amount of velocity to start with, comparable to the rest of it, right? And then it comes down and settles, it oscillates around 0. So right, we spike up, we move out of the way, and then it slowly approaches its steady state position, right, by slowing down. Then it hits steady state, and it's just going to kind of shake there, right? It's just going to kind of shake there. Ooh. You can come in here and pull signals off if you want to, right? That works and it's fine. What would you expect I to look like if you looked at the current? Now, I want to know what the current response is, right? Well, it looks a lot like the force, right? Which kind of makes sense because we just scaled the current to get the force, right? Scaled the current to get the force. That's it. Okay. You guys have any other questions on this? We are anything? No? Sure. yeah, so in the homework, right? I forget what number it is. I think it's 13. Homework 13, you have to do the motor model, right? You could do something like this if you didn't want to create the transfer function from one end to the other, right? I mean, you still have to, because part of the problem asks you specifically for the transfer function, right? But if you didn't want to model just the transfer function, you could certainly make subsystems of each and have them interplay with each other. All right. Any other questions? Nothing? Well, guess what? There's another thing we can do. I can use an M file to run a pre-existing Simulink model with parameters that I set up. So hey, check this out, right? And this, I believe this code is in your textbook. I believe so, right? And so we're going to set our parameters, right? We've got our solenoid electrical model right here. We've got the mechanical portion right here. And then we've got this guy, right, in this blue box right here, right? Run Simulink model. And if you use the command sim and then give it the name of your Simulink model, you don't even have to open Simulink. It will just run it. Literally minutes of your time saved from having to open Simulink. Minutes. Right? But this is nice, right? Why is this nice? Because we can plot directly in our code, right? So we don't have to waste time digging through very complex Simulink models to adjust all of our variables. We just do it here. We can print our plots to screen, right? Once you get your plots printed to screen, right, you could even save them from this code, right? You could use the save as command and save your plots as .figs, right? So you could have them for later. And then you could adjust your parameters and do it again, right? So you can see how changing specific parameters would affect the entirety of your system, right? So this is nice, right? And we'll talk a little bit about this again in a little while. Okay, what time is it? All right, so. When we come to the track wizard points for the week, you can earn up to 20. You can earn up to 20. Yes. So. Is it? I don't know. It could be. It could be very close to our lab. So what do we have here? All right, I'm going to give you guys, so I gave the other class 30 minutes, so it's only fair that you guys get 30 minutes, because I can't have, this is a tightly regulated competition. The Tri-Quizard committee would have me, or would string me out to dry. So you get 30 minutes to do this problem. There's a couple of things that I didn't tell you. I will throw them into Discord so you guys can get all the parameters, okay? You get 4 points for every one of the steps that you do correctly in the modeling process, right? So free body diagram, inputs, outputs, truths, reduction, and analysis, right? So there is an analysis portion. You should try to create a Simulink model for this, okay? Notice, it's giving you a hint here. It wants you, or I want you, to use state space, right? Because it says measure the velocity of the locomotive and the displacement Z1 minus Z2. So do this using a state space representation because I specifically want these two things as your outputs, right? All right, I will set up the breakout rooms. $30. Go. Man. Yes. You tell me, Noah. You tell me. Oh, we gotta do that. Probably do that. I guess if you really want the parameters. I guess. You guys want to check as you go, that's fine. You can check as you go. Mm-hmm. way we did it last class was at the end of the 30 minutes, everybody took one representative to the firm, showed me what they had. It's probably best. 4.5 minutes to bed.
Dr. D, you're muted. I don't know if you're trying to talk to.
That would explain it. Thank you. I forgot that when you come out of breakout rooms, I mute everybody, including myself, which seems like an oversight because this happens every single time. All right, so somebody from Zero Division, please flash what you got into the camera so that everybody can see.
Oh boy, here we go. I've got up to only like the ins and outs and truth stuff.
Okay, well, let's see it. Hold on. Say something, Blake, so your picture gets big.
Here you go. Is that it?
Yeah, what are your ins and outs?
FA of T, Z2 and Z3. My outs are Z1, Z2, and Z3.
So remember, your inputs are not going to be your. Yeah, never mind. You're good. You're good. You did globals and locals. We're good. I thought you said C instead of Z. Then it clicked in the screen, and I was like, man, awesome, good stuff. Cool. Thank you.
Yep.
Moving down. Does anybody want to volunteer or? All right, sanitizers. Yeah, your mic's not on. No. Here, just put it here.
We got all the way to the state space.
You're close, but your Y is off. Because Y, you needed to do the velocity of car one and the displacement Z1 minus Z2. That was in the problem center, but otherwise looks really good. Right there. All right. Okay, let's go with the Swarm Lords. Swarm Lords. Lords of the Swarm.
Yes. We got, honestly, we were building out we were reducing. I don't know, me personally, I made a lot of mistakes. I forgot that it was not, what's it called when it's connected to a ground. It was like a free spring, like a free damper. So I kind of did this wrong, so I had to go back and do that. And then we started we're turning it into the state variable equations, and yeah.
Okay, well, let me see a free body diagram. Let's start with that.
Oh.
That looks good. All right, and what's your inputs, your outputs?
The input, I said it was the F of A of T, and the output was Z1, Z2, and Z3.
Yeah, cool.
Yeah.
And then you guys started doing your reduction, but didn't quite get through it, right? Because you got turned around a little bit.
Yeah.
No big. All right, cool.
Yeah.
But
I finished the reduction, I will say that.
We're going to go through this one all the way from beginning to end, so we will. All right. Two left. 185.31. The cost of a ticket to Disneyland. All right, Jesse. Hold on, it's without your microphone. I've got to find your picture. Don't turn your microphone on though, because that'll mess everything up. There you go. Got it.
So I put my diagram and
Okay, so You guys were close on that reduction, right? But did you treat that as a free end spring or fixed end springs and dampers? It's got to be relative to the displacement, right? And the relative velocity. There. Right, from there, we need to go state space, right, and then, then we go into simulate, right? Okay. Uncalibrated calipers, who I haven't bothered to change the name yet on, I apologize, right? Hold on. I gotta unpin your video. I'll find my own video. It's all so complicated. All right, let's try that. All right, uncalibrated calipers. What we got?
I got up to the point where you can't even see because of my screen. Here.
Hold on, Jose. I gotta find your video.
I did the 6 state space equations. That's how far I got.
All right, so let's see.
I didn't really simplify them or anything. I just wrote it out.
Well, what you have looks pretty good. So, all right, cool. That's everybody. Good work. All right, so let's talk about it. Right. Well, hopefully everybody can see that now. Great. Good work, everyone. Good work. So I know it wasn't enough time to get through the whole thing, but in the in order to be fair to the class, since it was for points, they only got 30 minutes, so you only get 30 minutes. You guys are all about around, like, the groups that got farthest here were around the same point, right? So nobody typically gets into the Simulink in that amount of time, just because, including myself, right? You guys can see how doing these problems gets lengthy, right? All right, so, all right, here, this is the part that everybody did well, right? Y'all got good free body diagrams. Nobody fell into the trap of not having forces on both, like M1 and M2, right? Y'all have equal and opposite forces. Noah, your question from before, are these in extension or compression? The answer is yes, because it doesn't matter as long as you're consistent with writing your equations, because the signs will all work themselves out, right? The signs will all work themselves out. Okay. So I've got my truths, right? You need to have some semblance of this, right? My input is FA of T. You can also include Z, Z2 and Z3, right, if you wanted. But I decided to go global for this one, because it doesn't really matter. We're going to state space, so those intermediate inputs and outputs don't really affect us too much. All right, and then my truths, right, some of the forces, FK1, right, these are all, as Connor pointed out, right, these are all free-ended. And so, well, that's not entirely true. They're not all free-ended. The rolling friction, right, the rolling friction is fixed end, but everything else is free-ended. What's that? If the ground was also moving, right, that's the, you guys might remember from, I'm pretty sure there's a problem in ESG-455. Yeah, you've got the gear that's rotating, the double gear that's rotating on the rack. So the top rack is moving, and the gear is moving, and there's all sorts of fun. All right. Anyway, we can move into our reduction, right? Here's the results of the reduction. I didn't go through all the math here. If you guys want to use this as a way to practice reductions in state space, you have the solutions now, right? So you can do that. So these are the three equations that I got. It is sixth order, so that's fantastic. It's also the reason why we're not going to draw this response by hand, right? Because as much fun as that would be, we're just not going to. Even though we know that it's some combination of first and second order responses that are happening here. Okay, so I choose my state space variables, right? The general convention when choosing state space variables is to choose your energy storage elements, right? In this case, we have a spring and a mass. Those are both going to store energy. One will store energy with position. That is a spring, right? We stretch the spring, we store some energy, we let go, it dissipates. The mass stores energy by means of kinetic energy or the velocity, right? And that's why we chose Z1 and Z.1 as X1 and X2, right? So pick your X's, right? And then the X dots are easy because once you pick your X's, right? So X1 is Z1, X2 is Z.1, X3 is Z2, X4 is Z.2, X5 is Z3, X6 is Z.3, right? Then we just take the time derivative of each of those. Boom. So we can write down our state variable equations, right? We solve them. Again, I didn't go through the whole song and dance on the slide. You guys can double check them at your own leisure, right? These are how we're going to build our state matrices, our state space matrices. Of course. So on the lab, the question was, how in depth do I want you to go with how you made the model for a write-up? And honestly, I would like to see the whole thing, because that's where that's where the rubber meets the road to a certain regard for this class, right? Okay. So that's where we're at, right? So now we can build A, B, C, and D, right? Because if we're going to use state space, we need A, B, C, and D. But there's a couple of variables that I didn't put on here yet, right? U is FA of T. Right? And, we were told that Y1 was equal to Z.1. Well, that's just going to be X2. And Y2 was equal to Z1 minus Z2, which means it's going to be X1 minus X3. There's one more thing. I didn't use the input that I told you guys to. All right. I didn't use that input. So I'm going to go back and I'm going to tell you what my input was, because it's a nasty looking input. I used a step or a piecewise function. It looks like this. It looks like a rampant head, okay? But it's a little bit different. So it's going to be 2 times 10 to the 5th plus 5,000 t squared for 0 less than equal to t less than equal to 20. And 2.2 times 10 to the 6th for t greater than 20. Why did I choose that? Is that arbitrary? It's not. These parameters that we've been given, the parameters that I gave you, right, in Discord, aside from FA, are given in an ASME paper regarding locomotive coupling systems. So I found them in literature. Right. That paper is actually in one of the appendices of the textbook. Because this is problem 6.22 from your textbook. right? That's what this is. So this is what I use, right? So why would I use this? It's a little bit more realistic than a step, right? It's going to ramp up our force, and then it's going to hold it at a constant level, right? We're not expecting, again, nothing instantaneously has any amount of force, right? It's going to ramp, and this is just describing how this works. Okay, so that's the output or the input that I'm using. Right, so I've defined all my variables, right? I've got y, I've got u, I've got all my x's, right? I can make my state space matrices now, as long as PowerPoint obeys and moves to the next slide. That is. There we go. All right. Couple of things. Remember what we're trying to do. X dot is equal to AX plus BU, and Y is equal to CX plus DU. This is what we were trying to build. Also, I should have mentioned this when we were putting together the X dot equations, but remember, our state variable equations always take the form of X dot N is equal to some function of X1, X2, all the way out to Xn, and U1, U2, all the way out to U sub n, right? So this is saying that when I make a state variable equation, I need some derivative of a state variable that is a function of just my state variables and my inputs. That is what I'm looking for. And that is what we built on the previous slide, right? We can get rid of that one. We'll leave this here for right now. All right, so I'm not going to write out the full equation because I'm gonna have to write a pretty lengthy matrix on this one. So I'm just going to give you what A and B are, and then we'll discuss the output equation because that's a little bit more palatable when it comes to actually writing it out. Right? So let's look at this, right? So again, let's discuss this, right? So where I need the right mouse, that would help. Where did these equations that we wrote on the previous slide come from, right? Where did this x dot 1, x dot 2 come from? They come from us, first of all, x dot 1 is equal to x dot 2, or x2, right? Where does that come from? This relationship right here, right? X dot 1 is z dot 1, but we need everything in terms of a state variable and an input. Well, now it's in terms of a state variable, right? Same deal here. X dot 3 is x4, and x dot 5 is x6, all right? That's where those three came from. The other three come from us solving equation 1, equation 2, and equation 3, right? All we did was we took those three equations, we solved for the highest order derivative, and then we plugged in our state variables, right? That's what we did. And that's how we came up with these equations. And the nice thing about these equations, if you write them in a nice way and not the way that I've written them, where everything is just jumbled and all over the place, but if you wrote it as like x1, x2, x3, x4, x5, all the way up to x6 here, you would already have the A matrix because you just take the coefficients of each of those and you plop them in the A matrix where they're supposed to go. But I didn't do myself any favors here, and so, right, great. So when we go to write A, right, remember, we go to write A, this is going to be a beefy guy here today. I'm going to write it by column because otherwise I won't give myself enough room. And so we'll talk about it in a sec. Oh, sorry. Skip the line. My bad. So you get something for A that looks like this. It's a 6 by 6. Yeah, perfect. There is, and we'll talk about that in a second, but if you're going to do it a directed drop into Simulink, then you're going to have to do like a semicolon at the end of every row, right? But there is another way, and we'll talk about that in a second. Give me, I'm pretty sure I have to add a slide here. Give me 1 second. Oh, maybe not. Oh, I guess not. Okay, cool. So we need B now, right? We need B. Well, remember, X is X1, X2, all the way to X6. X dot is X dot 1 all the way to X dot 6, right? So if we need B, B is going to be a 6 by 1. And that's B. Where did we get B from? Let's roll it back 1 slide. B. The only equation that has U in it here, the only one is the X dot 2 equation. Everything else is 0 for you, right? There is no input on anything other than the X dot 2 equation. And so because of the way that we set up our matrices, right, that means that the second row of the B matrix has to be 1 over M1, and everything else has to be 0. No.
So you wrote it with just FAT as an input, but could you have done it with 2 more columns, B1 and B2?
No, because you have them defined as state variables, and so you get very strange dynamics. Remember, when we're talking about state space, we're talking about the state matrices are or the state equation is how we define our system, right? We're making a mapping between we're essentially making a way to predict what will happen based off of the energy storage of that, right? If you wanted Z1 and Z2 as an output, you could certainly have that as Y, right, in your Y matrix, right? But in terms of using local inputs, we don't do that for state space representation. Cool. All right. So, we have any questions on A and B? All right. Do you have any questions on A and B? All right. Again, you can use. I know I didn't go through the full solution on how to find these, right? If you want to run it back on your own and then come ask questions during office hours, that's fine. I'm more than willing to talk about that. But let's concentrate on this C matrix, right? So remember, Y is equal to CX plus DU, right? If we do this in the way that we normally do, we would have Y1 and Y2. This is going to equal some C matrix here. X1, X2, well, I'm going to need more room than that. This is actually going to look more like this. All right, so I've got something like that. Plus D. There's only one input. All right, so we've got a 2 by 1. In order to get a 2 by 1, right, what else do we have? Well, this is a 6 by 1. If I need a 2 by 1, then this needs to be a 2 by 6, right? Because the inner dimensions cancel and we'll be left with a 2 by 1. Okay? So we already know that because of the size of our state vector, we know that C has to be of a certain size as well. Okay, great. Y1, what was Y1, right? Let us recall that we said that Y1 was equal to X1. Well, all right. And there was no U. Y2 was equal to X1 minus X3, right?
I think I have written down X1 X1 dot.
Oh, dot. So it equals X2 then. My bad. There. Now we're good. It equals X2, right? Why? Because it's the velocity of the locomotive. We got 1 over. All right, so Y2 is X1 minus X3, right? So, okay. 1. All right, we've got 0 for X2. All right, so linear combinations work like this, right? So I've got 0, when we do row times column, I've got 0 times X1 plus X2 times 1 plus 0 plus 0 plus 0 plus 0, right? So if I need to get out of this X1 minus X3, I need something that looks like this, right? 1 times X1 minus, or plus 0 times X2 minus 1 times X3 plus 0 plus 0 plus 0. I'm left with X1 minus X3. This will give me the distance I need, right? And there's no U. So C is this, and that's D. Output matrix, the output equation always seems like it's fudged, right? It always seems like Dr. D is just making this up as he goes. And kinda, yeah, right? Because I determined what I wanted the outputs to be, right? So, right, in real life, like why would you do this, right? Well, in real life, if you're going to use this as a means for implementing a control system, you need to know what your position is, right? So in real life, these things will be measured by sensors, right? These things will be measured by sensors. What is this displacement x1 minus x3, right? Z1 minus Z2, what is that? Well, you guys, I'm gonna use this example, and it comes from not real world, but I think it illustrates it very well. You guys have all seen those scenes in the movies, where there's like guys on a train, and you got to pull the pin, right? And then the train like separates. That's what we're measuring the distance between those cars, right? In the real world, they're connected by some sort of spring damper system, right? Because keeping that rigid wouldn't make sense. It needs to be able to grow, to expand and contract, especially when it goes around curves, right? And so we're measuring that displacement between the two cars as it changes as a function of time. Okay? So let's take a look at the Simulink, because that's what everybody really wants to see, I know. Simulink. That looks gross. This looks super gross. Check it out, Trevor. Look, I have these defined as A, B, C, and D. I'm actually going to enter these in MATLAB. Why? Because it's way easier to do that way. Because you're right. Entering this as one line is going to be a pain in the butt, right? So I've got these things set up, right? So what is going on here, right? Remember, my input was what? My input was 2 times 10 to the 5th. Right? Well, what's 2 times 10 to this is the 2 times 10 to the 5th. This step is just turning on at 0, right? So it's 2 times 10 to the 5th plus 5,000 t squared. Well, that's this. I'm taking this clock, running it through a square block to get t squared, multiplying it by a gain of 5,000, and I'm adding those two things together. And then it goes into a block that we haven't used before. Right? It goes into a saturation block. And what's the saturation block going to do? It's going to saturate my signal. What does that mean? Well, it means that it's going to cap it. It's going to cap it. This saturation sets a maximum, and it says my upper limit is 2.2 times 10 to the 6th, and I will never go above that. So any force that you say is higher than that, it will just cap. Right? It's an electronics term, right? We saw it when we talked about op amps in the op amp video, right? If you give an op amp too much, it's just going to tell you that you hit 12 volts, right? It's going to tell you to hit whatever the max voltage is, right? Because it cannot read above that. Same deal here, right? We're just saying once our force reaches this level, it will always stay at this level. Okay? Now, if you do the math, and you plug 20 seconds in there, guess how much force you get at 20 seconds? 2.2 times 10. So after 20 seconds, it stays at that level. All right, so that goes into my state space block. Magic happens, right? You know, animal sacrifices, all those things. And then we use this other block that we haven't talked about, right? This black line. That is the demux block. So with the demux block, what is the demux block going to do? It's going to demux my signal. That's not helpful, right? That's not a helpful thing to say, Dr. D. Why would you say that? Because now you know how I feel when I ask for definitions and you just tell me the words back in a different order, okay? But what does it do? It takes this signal Y, right? And Y is an array, right? Y has two components. It's got Y1 and Y2 in it. And it splits that vector into two different signals. And then we read it out to our workspace as Y1 and Y2, right? We could also read it to scope, but we're not going to do that because instead we're going to do this. I have a code. I have a code to run. All right, check it out. I've got M1, M2, M3, K, B, and BR. All right, these are based on the JD SMC 1974 paper by Genin et al. I was wrong. It wasn't ASME. I apologize. I'm probably going to get sued now. All my videos will be taken off of YouTube. And there's that. Right here. Right, we can do our state space representation. Right, Z1 is my locomotive position. Z2 is my car 1 position. And Z. So slightly different Z variables. Or X is Z1, Z dot, right? So telling you what my state variables are, what are my actual variables. And this is how we set up our A matrix, right? I did it by rows. A row 1, A row 2, 3, 4, 5, and 6. And then I created one matrix that concatenates all of those together, right? B, C, and D were fairly small, so it didn't need that treatment. Right? Another way you could do this, right, if you really wanted to, you can say, should work in it. Right. You do have to give it the semicolon after that. Oh, not going to do it now. But you should be able to use an ellipsis to get it going. Right. Then what do? I hit run sim. Right. Well, I don't hit run sim. I type sim and then the name of my simulant model. This is going to load all of my variables, right? It's going to pull my simulant model up. It's going to run it. And then it's going to plot some plots here, right? Figure 1 and figure 2. So let's run it. See what happens. Probably get errors. It did not get errors. Shock. So let's talk about figure 1. Hey, here's figure 1. This is MATLAB popped it out for me, right? Because I coded it good, but still. This is my locomotive speed in meters per second, right? And so you see we've got this small startup portion, then it ramps up pretty significantly, and then it stabilizes around 24-ish meters per second in about 21 seconds, something like that. So we lag behind our force input a little bit, but we would expect that, right? We would expect. What about that displacement, the relative displacement of the two cars? This one's pretty interesting because we've got some oscillatory effects at the beginning, right? So when it starts to move, right, the back cart's going to try to catch up a little bit until it actually overcomes the spring force and the friction enough to get some separation. Then it's going to ramp up pretty heavily, and then it's going to have about 20 seconds stay constant. Okay. I'm sorry, say that one more time, Joe. So in terms of the lab, essentially, yeah, you're going to model this. You are going to, right, you're not going to use that input that I use, right, because it's not a train. But you're going to model your system, right? You're going to then compare that to what the final, like, what is the position of the third cart? Oh, I'm going to give you, yeah, you know how much amperage is given. I'm going to give you the torque, the IT curve, right? The power curve for the motor that gives you all that stuff. So you can figure it out. You can figure out the initial torque. Right? All right. You guys have any other questions?
I have a question about the simulator.
Yeah.
You have like the Y, and you have two spots on like right around here. What were those?
Oh, those were two workspace blocks. Yeah. I just sent it to the workspace. Is that? Okay. We got any other questions? So the other thing that's nice about having that code, right, is if I wanted to see how things change, right? So what if I want to change my damping, right? What if I want to change my spring, right? You just quickly do it and it's done, right? You run it again. That took very little amount of time to run, right? So it's pretty versatile in that way. All right, we got homework. Okay. Too many mice. Too many mice. Homework 4 this month Sunday, right? Lab next week. homework 5 the week after, and exam 2 on the 24th. I will post homework 5 on Monday, right, so that everybody can have it. And again, if you need me over the weekend and you can't come to office hours tomorrow from 3 to 5, right, email. Email is probably the best way to do that. So, also, you can work together, right? That's allowed. So, talk to each other too. All right. Topic 5. What's up? Yeah, that was just the recap from last class. All right, I mean, it's recap-ish. We tied up some simulating stuff. So we're not going to be so heavy with simulate the rest of the semester, but still should bring your laptops and stuff because we are going to sometimes use MATLAB and Simulink to kind of illustrate some things. And I think it's helpful for you guys. Right, so topic 5, the Laplace transform method. What are we going to be able to do when we're done here? First, we're going to be able to develop mathematical models of both circuits and op-amp systems using the impedance method, right? So we're going to go through the impedance method, which is based on the Laplace transform method. And it's awesome because it makes circuit analysis a lot easier, in my opinion. The unfortunate part about this part of the topic is that impedance is not covered in your textbook, okay? But there is a reference on LoudCloud in the, if you look in the path, right? Course resources, I think it's something like that. There you go, yeah. Course materials. We will be able to apply mastery of integration, separation of variables, and the Laplace transform method in the solution of system models. We want to develop the correct inverse Laplace transforms using expansions and transform properties. We're going to contrast the differences between free, forced, transient, and steady state components of the complete response. Well, I mean, that was the last topic. We can do that already. And we know the difference between those things. We want to identify a transfer function when given a linear model expressed as both a single equation and a system of equations. We want to validate all of our solutions using MATLAB. And we want to analyze systems that are in transfer function and block diagram form. Seems like a lot of things, but it's going to be all right. We got a couple weeks, right? We'll do all those things today. And then the rest of the time, we're just going to not do anything, right? Yeah. All right, so do you guys remember? Do you remember how we used transfer functions to represent system dynamics in chapters 5 through 7? Do we remember? Sad face. Sad face. So we don't remember it. Well, it was called the time domain transfer function, right? It had the capital D in it. But what if we had a more formal, more better way of talking about transfer functions? What if? Well, we do, right? And that is what the Laplace transform offers us. The Laplace transformation offers a systematic approach for solving LTI systems by transforming the variables into algebraic equations in the complex Laplace domain. Right, so we're going to go from, this is a mapping, right? This is a mapping. We're mapping what we know about the time domain, how we think about things as being a function of time, and we're going to take that information and we are going to transform it through the Laplace transform to the complex plane, to a real and imaginary axis. Why? Why would we want to do that? There's a couple of reasons why. We'll go over them, right? But remember, when we talk about the root response of a system, we were talking about the real and the imaginary parts of our roots, right? So keep that in mind, right? Any existing initial conditions are handled in a systematic manner, and the system's response can finally be obtained by taking the inverse Laplace transform. So here's the order of events, right? We take the Laplace transform of a function. We take the Laplace transform, right? So when I say a function, I mean of our of our model, right? We take the Laplace transform of our model. We also take the Laplace transform of the input to our model. We create the transfer function. We solve it for the output variable. And then we take the inverse Laplace transform of that solution to get the time domain solution back. And what ends up happening is we end up doing algebra to solve ordinary differential equations. That's what ends up happening. Here's the definition of a Laplace transform. It converts a time domain function, f of t, into a complex variable s, right? So the script L, that fancy L there, that is the Laplace transform operator. Laplace transform curly braces f of t, some function of time, becomes capital F of s, right? Becomes capital F of s, right? So when we transform, if you see a capital letter, typically that is going to be our Laplace transformation. And if it's lowercase, it's in the time domain. This is equal to the integral from 0 to infinity of the function inside of the curly braces times e to the negative s t dt. Now I know what you're all thinking right now. Dr. D, that is an improper integral. You cannot evaluate something at infinity. It is not possible. You watch me. Watch me do it. Okay? No, you're right? But it's not really, don't think of it as evaluating it at infinity. Think of it as you're taking the limit of this integral as we approach infinity. Right? We're taking it from 0 to the limit as we approach infinity. Okay? The Laplace transform variable s can be broken down into sigma plus j omega. Sigma plus, that's just the real plus the imaginary component. When we talked about roots, our roots have real and imaginary components, right? So does this tell us something about the characteristic roots of the system? And the answer is that we already know is yes, right? Why? Because we know that the denominator of my transfer function is the characteristic equation, and the roots of the characteristic equation are what we're going to be able to get out from our transfer function, right? When we solve for s. Slightly less helpful is the definition for an inverse Laplace transform, which tells us that the inverse Laplace transform of f of s is equal to f of t, right? So if I take the inverse, the Laplace transform inverse of my Laplace variable, I'll get f of t back. Not super helpful, right? Does not give us any information about how we're going to do it. But spoiler alert, it involves partial fraction expansion, which, as I told my morning class, is in my top 5 most favorite expansions of all time. Okay? All right. Some notes on roots and complex numbers. Now, we're going to go over most of this information again, and we have gone over some of this before. Right, but many of the systems that you encounter are second order or higher. Right, real world things are going to be second order or higher, likely, especially if you start adding control systems, because control systems add orders to systems. Right, but the roots of the characteristic polynomial will probably be complex. Right, we're going to have some complex polynomial, and that's what I'm showing in this plot here, right? So imagine z is the root of my, right, this one right here with the red lines around it, right? This point here is some root, right, that has a real and an imaginary component, right? If you think of this as a vector coming out from the center, right, this vector has an angle off of the x-axis that we can define. We talked a little bit about this when we went over our root responses, right? Things on a radial line. Right? Things that are at the same angle all have the same zeta, right? Things that are the same on a radial line all have the same zeta, right? Things in a circle all have the same omega n. right? Because the radius defines omega n. This height right here, this length is omega z, my natural frequency. Right, so these all belong somewhere, right? We all know these things. We've got in the top right, we've got also in my top 5 expansions, the Taylor series expansion, right? That's 2 of my top 5, right? If you want to know the other 3, you got to come to all the rest of the classes. That's how it works. It's incentivizing you, right? It's the worst incentive in the world, but there it is. All right. So what do we've got here, right? We've got Taylor series. We've got the Euler or the Euler identities, depending on how you want to say that. Those are going to be important when we get to frequency domain analysis, right? But e to the j theta is cosine theta plus j sine theta, and e to the negative j theta is cosine theta minus j sine theta. And these are some properties here, right? We've got some limits of exponentials, right? And these are important too, because these are going to come up quite a bit, especially when we start taking Laplace transforms of things, right? Because you need to take the limit as e to the st goes to infinity, right? Or e to the negative st. So if you take the limit as x goes to infinity of x to the x times e to the negative x, right, you go to 0 if x is real. And you go, right, and so same deal, limit of time going to infinity, e to the negative st is 0 as long as s is positive. The things under here, right, these guys are all general properties of complex numbers that we'll talk about if and when we do. So we watch a video.
I'll now introduce you to the concept of the Laplace transform. And this is truly one of the most useful concepts that you'll learn, not just in differential equations, but really in mathematics. And especially if you're going to go into engineering, you'll find that the Laplace transform, besides helping you solve differential equations, also helps you transform functions or waveforms from the time domain to the frequency domain and study and understand a whole set of phenomena. But I won't get into all of that yet. Now I'll just teach you what it is. Laplace transform. I'll teach you what it is, make you comfortable with the mathematics of it, and then in a couple of videos from now, I'll actually show you how it is useful to use it to solve differential equations. We'll actually solve some of the differential equations we did before using the previous methods, but we'll keep doing it, and it'll solve more and more difficult problems. So what is the Laplace transform? Well, the Laplace transform, the notation is the L, like Laverne from Laverne and Shirley. Might be before many of your times, but I grew up on that. So actually, I think it was even reruns when I was a kid. Maybe, well, anyway. So Laplace transform of some function, and here the convention, instead of saying f of x, people say f of t. And the reason is because in a lot of the differential equations or a lot of engineering, you actually are converting from a function of time to a function of frequency. And don't worry about that right now if it confuses you. But the Laplace transform of a function of t, it transforms that function into some other function of s. And how does it do that? Well, actually, let me just do some mathematical notation that probably won't mean much to you. So what is a transform? Well, the way I think of it is kind of a function of functions, right? A function will take you from one set of, well, in what we've been dealing with, one set of numbers to another set of numbers. A transform will take you from one set of functions to another set of functions. So let me just define this. The Laplace transform, for our purposes, is defined as the improper integral. And I know I haven't actually done improper integrals just yet, but I'll explain them in a few seconds. The improper integral from 0 to infinity of e to the minus st times f of t. So whatever is between the Laplace transform brackets, dt. Now that might seem very daunting to you and very confusing, but I'll now do a couple of examples. So what is the Laplace transform? Well, let's say that f of t is equal to 1. So what is the Laplace transform of 1? The Laplace transform of 1, so if f of t is equal to 1, it's just a constant function of time, well, that will be equal to, and let me rewrite, well, actually, let me just substitute exactly the way I wrote it here. So that's the improper integral from 0 to infinity of e to the minus st, e to the minus st times 1 here. Well, I don't have to rewrite it here, but there's a times 1 dt. And I know that that's probably, that infinity is probably bugging you right now, but we'll deal with that shortly. Actually, let's deal with that right now. This is the same thing. This is the same thing as the limit, and let's say as a approaches infinity, of the integral from 0 to a e to the minus st dt. So this is, just so you feel a little bit more comfortable with it, you might have guessed that this is the same thing, because obviously you can't evaluate infinity, but you can take the limit as something approaches infinity. So anyway, let's take the antiderivative and evaluate this improper definite integral, or this improper integral. So what's the antiderivative of e to the minus st with respect to dt? Well, it's equal to what? Minus 1 over s e to the minus st, right? If you don't believe me, take the derivative of this. You take minus s times that would all cancel out, and you'd just be left with e to the minus st. Fair enough. And we're going to take, actually, let me delete this here to use some of that real estate. We are going to take the limit as a approaches infinity. You don't always have to do this, but this is the first time we're dealing with improper integrals, so I figured might as well remind you that we're taking a limit. And we're going to evaluate, we took the antiderivative, now we have to evaluate it at a minus the antiderivative, evaluate it at 0, and then take the limit of whatever that ends up being as a approaches infinity. So this is equal to the limit as a approaches infinity of, okay, if we substitute a in here first, we get minus 1 over s. Remember, we're dealing with t. We took the integral with respect to t. E to the minus s a, right? That's what happens when I put a in here. Minus. Now what happens if when I put t equals 0 in here? So when t equals 0, it becomes e to the minus s times 0. This whole thing becomes 1. And I'm just left with minus 1 over s. So I had minus 1 over s. Fair enough. And then let me scroll down a little bit. I wrote a little bit bigger than I wanted to, but that's okay. So this is going to be the limit as a approaches infinity of minus 1 over s e to the minus s a minus 1 over s. So plus 1 over s. So what's the limit as a approaches infinity? Well, what's this term going to do? As a approaches infinity, the exponent is going to get, if we assume that s is greater than 0, and we'll make that assumption for now. Actually, let me write that down explicitly. Let's assume that s is greater than 0. So if we assume that s is greater than 0, then as a approaches infinity, what's going to happen? Well, this term is going to go to 0, right? E to the minus a Google is a very, very small number, and a e to the minus Googleplex is a very even smaller number. So then this e to the minus infinity approaches 0, so this term approaches 0. This term isn't affected because it has no a in it, so we're just left with 1 over s. So there you go. This is a significant moment in your life. You have just been exposed to your first Laplace transform. Eventually, and I'll show you in a few videos, there are whole tables of Laplace transforms, and eventually we'll prove all of them. But for now, we'll just work through some of the more basic ones. But this can be our first entry in our Laplace transform table. that the Laplace transform of f of t is equal to 1 is equal to 1 over s. Notice we went from a function of t, although obviously this one wasn't really dependent on t, to a function of s. I have about 3 minutes left, but I don't think that's enough time to do another Laplace transform, so I will save that for the next video. See you soon. Let's keep doing some Laplace transforms. One, it's good to see where a lot of those Laplace transform tables you'll see later on actually come from. And it just makes you comfortable with the mathematics, which is really just kind of your second semester calculus mathematics, but it makes you comfortable with the whole notion of what we're doing. So first of all, let me just rewrite the definition of the Laplace transform. So it's the L from Laverne and Shirley. So the Laplace transform of some function of t is equal to the improper integral from 0 to infinity of e to the minus st times our function of t, and it's with respect to dt. So let's do another Laplace transform. Let's say that we want to take the Laplace transform. And now our function f of t, let's say it is e to the a t. Laplace transform of e to the at. Well, we just substituted into this definition of the Laplace transform. So that is equal to, and this is all going to be really good integration practice for us, especially integration by parts. Almost every Laplace transform problem turns into an integration by parts problem, which, as we learned long ago, integration by parts is just the reverse product rule. So anyway, this is equal to the integral from 0 to infinity e to the minus st times e to the at, right? That's our f of t dt. Well, this is equal to just adding the exponents because we have the same base. The integral from 0 to infinity of e to the what? A minus s e to the a minus s t dt. And what's the antiderivative of this? Well, that is equal to what with respect to t? So it's equal to 1 over a minus s. That's just going to be a constant, right? So we can just leave it out on the outside. 1 over a minus s times e to the a minus s t, and we're going to evaluate that from t is equal to infinity, or the limit as t approaches infinity, to t is equal to 0. And I could have put this inside the brackets, but it's just a constant term, right? None of them have t's in them, so I can just pull them out. And so this is equal to 1 over a minus s times. Now, what is the limit? We essentially have to evaluate t as at infinity. So what is the limit at infinity? Well, we have two cases here, right? If this a minus s is a positive number, if a minus s is greater than 0, what's going to happen? Well, as we approach infinity, e to the infinity just gets bigger and bigger and bigger, right? Because it's e to an infinitely positive exponent. So we don't get an answer. And when you do improper integrals, when you take the limit to infinity and it doesn't come to a finite number, the limit doesn't approach anything, that means that the limit, or actually the improper integral, diverges. And so there is no limit. No limit. And to some degree, we can say that the Laplace transform is not defined when a minus s is greater than 0, or when a is greater than s. Now, what happens if a minus s is less than 0? So if a minus s is less than 0, well then this is going to be some negative number here, right? And then if we take e to an infinitely negative number, well then that does approach something. That approaches 0, and we saw that in the previous video. And I hope you understand what I'm saying, right? E to an infinitely negative number is 0, or it approaches 0, while e to an infinitely positive number is just infinity, so it doesn't really converge on anything. So anyway, so if I assume that a minus s is less than 0, or a is less than s, and this is the assumption I will make, just so that I get, so that this integral, this improper integral, actually converges to something. So if a minus s is less than 0, then this is a negative number. E to the a minus s times, well, t, where t approaches infinity, will be 0, minus this integral evaluated at 0. So when you evaluate this at 0, what happens? T equals 0. This whole thing becomes 0. E to the 0 is 1. E to the 0 is 1. And we are left with what? Minus 1 over a minus s. And that's just the same thing as 1 over s minus a. So we have our next entry in our Laplace transform table. We have our next entry, and that is the Laplace transform. The Laplace transform of e to the a, e to the at is equal to 1 over s minus a, as long as we make the assumption that s is greater than a. This is true when s is greater than a, or a is less than s. Either way, you can view it either way. So that's our second entry in our Laplace transform table. Fascinating. And actually, let's relate this to our previous entry in our Laplace transform table, right? What was our first entry in our Laplace transform table? It was Laplace transform of 1 is equal to 1 over s, right? Well, isn't 1 just the same thing as e to the 0? So we could have said that this is the Laplace. I know I'm running out of space, but I'll do it here in purple. We could have said Laplace transform of 1 is the same thing as e to the 0 times t, right? And that equals 1 over s. And luckily, it's good to see that that is consistent. And actually, remember, we even made the condition when s is greater than 0, right? We assume that s is greater than 0 in this example. And lo and behold, here again you say s is greater than 0. This is completely consistent with this one, right? Because if a is equal to 0, then the Laplace transform of e to the 0 is just 1 over s minus 0. That's just 1 over s. And we have to assume that s is greater than 0. So really, these are kind of the same entry in our Laplace transform table. But it's always nice in mathematics when we see that two results we got trying to do slightly different problems actually are in some ways connected or the same result. Anyway, I'll see you in the next video, and we'll keep trying to build our table of Laplace transforms. And maybe 3 or 4 videos from now, I'll actually show you how these transforms are extremely useful in solving all sorts of differential equations. See you soon.
Hey, Dr. D, you're still muted.
That should be better. So we want to find the Laplace transform here, right, of this. So we have our fancy script L, our curly brackets, right, AE to the negative AT. By definition, right, this is the integral from 0 to infinity of A e to the negative AT times e to the negative st dt. By definition, this is what we want to be doing, right? We need to take this. Well, I can do a little bit of simplification here, right? I can take my a outside of the integrand, and I can rewrite the exponential like this. All right, so all I've done is just, rearrange this a little bit, right? The constant can get pulled out, and I just say, well, you know what, e to the at times e to the st, well, I can maneuver those together, right? And they become negative s plus a times t. So I can take, right, I'm not going to do the step in the video where the guy does the limit as, right, we can understand that if you see, right, you see this, we're going to evaluate this from 0 until the limit as t approaches infinity. And if we do that, right, we'll get what? Well, we've got to take the antiderivative of this, right? We need to take the antiderivative. Well, that's just going to be a over, well, negative s plus a, e to the negative s plus a times t, evaluated between 0 and the limit as t approaches infinity. So let's evaluate that then, right? So what do we end up with? We end up with the limit as t approaches infinity. Well, I'm not even going to bother writing that. We end up with e to the negative infinity minus a over negative s plus a, e to the 0, right? Remember, this is going to go away, right? This whole term goes to 0 because e to a very small number. All right, what's e to the negative infinity? Well, it's the same as 1 over e to the infinity, which makes it about 0 in the limit, right? So we're just left with negative a, right? We're left with negative a over negative s plus a, or a over s plus a, which is equal to f of s. And that's what we're left with. And that's what we get. Great. So the question was asked last class. How does this help us? That's a great question. Taking the Laplace transform by itself doesn't necessarily help us. But when we do this to our system equations and we find the transfer function and then we use the inverse Laplace transform, that's what helps us. Okay? Applying this in this way just to get the mapping is great, and it's something we need to be able to do. But this by itself isn't the whole story, right? Okay. Take a look at this. The one in the video that we did was e to the negative at, right? Or e to the at, not e to the negative at, right? And what did we get out of that? That was supposed to be 1 over s plus a, right? Something like that. Notice, this is the same, except that we have that scaling factor there, that a, right? So the Laplace transform of some constant times e to the negative at is the same as a times the Laplace transform of e to the negative at, right? The Laplace transform is a linear operator, and next class we will talk more about the properties of the Laplace transform and what we can actually do with it. Okay? Great success. We're done for today. I'll put up the thing. I forgot to put up the other thing for the end of the week. I apologize. But the same rules apply, right? If you're not feeling comfortable with the stuff that we're doing in class, then please make sure that you're coming to office hours, right? I've got office hours Tuesday, Wednesday, and Friday from 3 to 5 p.m. and Monday mornings from 9 to 11 a.m., right? Or if those times don't work, contact me and see if there is a time that will work, right? I can meet on some days outside of those times.
A couple questions.
Yeah.
be more consistent about 13. So I keep getting to right there. So let's play it all out. But then I feel like that's a lot to have as part of the Laplace transform. Or yeah, it's a fixed performance. So I feel like I need to have more on that side, but I can't really do anything with that without applying it to that PL.
Which, remember, CL is a constant. So overall, this could be considered, right? So you're not going to like it, or what you're going to. So the typical, the way that we do this, the CL is technically considered an input. And in order to get a transfer function, right, you can ignore in multiple inputs, you can ignore the effect of one and get the transfer function just the other. So if you set CL to 0, right, then you can get this transfer function of this out. The other way that you can do this is you would have to get the comment. You have to get the comment.
So I can
You can ignore that.